Okay, this is the second in the series of wave, sound, and light notes. Given we don't have lecture, there's your opportunity to hear some of the stress points that I have for this unit. So we're going to continue on with some aspects of all simple harmonic motion. SHM is simple harmonic motion. So this includes waves, but this includes anything that vibrates. This could be your pendulum, like we did the pendulum lab earlier in the year, or anything that moves back in a regular formation. This springs, we talked about springs a little bit earlier. So they have an amplitude. So there's a maximum displacement of that oscillating thing from the equilibrium position, and that's measured in meters. It's how many meters away it is from its starting position. So you think about your pendulum, you can measure how far away it started, or your spring, you can measure how far away it started from where it began. So, and that corresponds to the amount of energy that the system has. That's going to be important for waves as we move forward. The period is the amount of time that completes one cycle. Units would be seconds or seconds per cycle. And again, we measured the period of our pendulum, the amount of time that it took to swing back and forth. The frequency we haven't talked about yet is the opposite of period. So for period, it was the amount of seconds per cycle. For frequency, it's actually the amount of cycles per second. So they're inverse of each other. And cycles per second is hertz. And again, so cycles per second is hertz, which is a new unit for you. Because these are inverses of each other, the equations are such. So period is the inverse of frequency, and frequency is the inverse of period. And again, those are on your reference table. So moving forward, speed of the wave. We spoke about speed earlier in the year as velocity equals distance over time, or speed equals distance divided by time. Units for that are still meters per second, or any unit of length over any unit of time. As we move into waves, there's some specific equations for wave speed. Probably the most important equation in this entire unit is velocity equals frequency times wavelength. So the frequency is the unit for frequency is hertz, which is waves per second. Wavelength is meters per wave. So I have waves on the top of frequency and the bottom of meters. The bottom of wavelength. So the waves cancel, and I'm left with meters over seconds again. So this, from a unit standpoint, is dimensionally sound. Because the frequency and periods are inverses of each other, I can also substitute in for frequency above to get velocity equals wavelength over period. And let me stress here, there's two T's on the screen. The lowercase t is time, the uppercase T is period. So they're both measures of time. Little t is the total time, where big T is the the time for a specific wave or a specific cycle. Speed of sound is 331 meters per second squared, and that can change given temperature, given pressure, given medium that we're traveling through. So that's the speed of sound in air, whereas the speed of light in a vacuum, or the speed of light in air, is pretty much 3 times 10 to the 8th meters per second. So if you think about this, there's a huge difference in these two measures. So, it's 3 times 10 to the second versus 3 times 10 to the 8th. So big difference in speeds here, which is part of the reason why if you are at watching fireworks, you see the fireworks far before you hear the fireworks, or if you're in a lightning storm, you see the lightning far before you hear the thunder. Now, this number down here, 3 times 10 to the 8, is really important. It's actually important enough that it gets its own variable c. C as in E equals mc squared. So, we'll talk more about both of these values and what contributes to these values as we get into sound and light later in the unit. So moving forward, I've got a practice problem here. If you were given the wavelength and the period, if I ask you to find the frequency is simply the inverse of the period, so 1 over period, which gives you 264 hertz. If I did velocity, I couldn't use distance over time here, but I could use either wavelength times frequency here, or wavelength divided by period. Both will work if you have 343, which is again about the speed of sound depending on the conditions. Reflection of pulses. So the next couple things we're going to talk about, I have a great lab that you could experience these, but unfortunately you're not going to have that opportunity here. So the reflected pulse, if I have a pulse that hits a unfixed endpoint, an endpoint that has the ability to move, that pulse that comes down on the one side will then be reflected back on the same side that it came down on. So it's not inverted, where if I have a fixed endpoint, which is the case most of the time where we're going to have a wave, is when it comes in, it will hit the fixed endpoint and then it will invert and reflect back on the other side. And again, these are wave pulses. These are pretty important for another topic we'll talk about later, but these are specifically for, these are, a general relationship for all waves, whether they hit a fixed or an unfixed endpoint. We'll talk about the applications of those later. This is an important one. So now I have two pulses interfering. So with two pulses interfering, I get what I call constructive or destructive interference. So I'm going to talk about the constructive first. So notice each of these wave pulses has an amplitude of 0.5. They're both 0.5 down. When they add together, the amplitude comes up to a -1. So they add constructively so that they're gonna add their amplitude. So here we've got 0.5, 0.5, they go up to 0.1. Notice what doesn't change is the wavelength in the process. The wavelength stays the same. Now, if they're on opposite sides, I get destructive interference. So I get a full sine wave right before they hit. I get total flatness, and then I get a full sine wave again. So it's really difficult to see destructive interference, but that's what happens. You can watch it again. So it goes, this is constructive, higher amplitude, same wavelength, and then on destructive, I'm going to have a full sine wave, total flatness, and then full sine wave. So it happens really quick, so it's hard to see. So again, these are constructive and destructive interference. So here's another picture of constructive. I have a wave with an amplitude of 2 and a wave with an amplitude of 1. I add those two amplitudes together and I get, so this is right before they meet. Right when they meet, I get an amplitude of 3. And then this is an important point that you couldn't see very well in the last simulation. After the wave pulses interfere, the wave that was going to the right, the big wave, is going to continue to go to the right. The wave that was going to the left, the little wave, is going to continue to go to the left. So, and then with destructive interference, again, I have an amplitude of 2, an amplitude of -1. This is right before they interfere. When they interfere, my 2 and my 1 are superimposed on top of each other, and the net wave formation is a wave with an amplitude of 1. Again, the wavelength doesn't change. It's just the amplitude that changes in this process. And again, the big wave continues to the right, little wave continues to the left. This is not complete destructive interference because there's still some amplitude left. But this is indeed destructive interference. So we're going to talk a little bit about waves being in phase. So if waves are in phase, they're in the same point in their wave cycle. So this is actually an old Regents question here. The picture was shown, said which points are in phase. Now, a lot of people think that G and E are in phase because they're both at equilibrium. That's not the case because E is on the way up and G is on the way down. B and D might be an answer choice, but B's at the crest, D's at the trough. A and C are at the same amount of amplitude or the same displacement, but again, one's on the way up, one's on the way down. So the only points that are in phase here are C and F. They're both in the same place in the wave cycle, both heading down. So another Regents question is, how many degrees out of phase are these two waves? So to think about this, we can take a look at one wave. So if I take a look at wave A, a complete wave goes out 4 lines. 1, 2, 3, 4. So a complete wave is 360 degrees. So if I divide that by 4, each segment is 90 degrees. So now if I go back and I look at wave A and the crest of A here and the crest of B here, notice those are 90 degrees out of phase. So the correct answer here is that they're 90 degrees out of phase. So interference, so I have 2 red waves, a wave with an amplitude of 2 and a wave with an amplitude of 1. So now if those 2 waves are together, these aren't just wave pulses, but these are complete waves. I get a resultant wave of greater amplitude. I get a greater amplitude in the positive displacement, and I get a greater amplitude in negative displacement. This is constructive interference. This is destructive interference. So this is positive 2 and negative 1. The net wave is going to be 1. The net wave is going to be negative 1. Again, the two wave formations, the full waves, interfere to either act constructively up above or destructively below. Now, this is really important because this is when we get two wave formations that come together, we often get what's called a standing wave. So here on the bottom, this is called a standing wave. It's the result of this wave moving this direction and this wave moving this direction. These two waves that are moving independently have the same frequency, amplitude, and wavelength. So if you can see, there's points where, so this point right here, when we have one wave up, we have the other wave down, when we have, and vice versa. So when I have the trough here, it's got the crest here, and they totally cancel out. When I have an equilibrium here, I have equilibrium down below. So the net resultant for this standing wave is always 0. There's no displacement. Now, the place on the wave that experiences complete destructive interference is called a node. So that's a node. The place on the wave that experiences complete constructive interference is called an antinode. So here's an antinode. So these meet when I have down and now up, and then down and then up. So when they're both up, I get a big up wave. When they're both down, I get a big down wave, and it alternates between the up and the down formation. And again, this is called a standing wave, this formation here. If I look at this, I've got 1, 2, 3, 4, 5, 6, 7 antinodes, and then I have 1, 2, 3, 4, 5, 6, 7 nodes. We'll talk more about this as we move through the unit. So, standing wave, if I were to have fixed endpoints on both ends, I can get standing waves in a variety of patterns. I can get this, which is a half of a wavelength. So if I go up and then I go down, a full wave would take me out to here. So this is half of a wavelength. This is a full wavelength. This is a wave and a half. This is 2 waves. Again, 2 complete waves. You got to go up and down to get through the full cycle. We'll talk about the implications of this a little bit more when we get to harmonics and sound later in the unit. So all things want to vibrate. All things that do vibrate want to vibrate with a natural frequency. And again, this isn't just for waves. This is for all vibrating objects. We did the pendulum. The pendulum vibrated with a natural frequency. It always vibrated with the same frequency or the same period based on the parameters of the pendulum, which again was the string length. Again, we talked about that when we did this lab back in the energy unit. Other things that might vibrate is a tuning fork. I'm not sure if you'll have the experience with real tuning forks this year, but a tuning fork, when you hit it, it vibrates back and forth, and the tuning forks actually have the frequency printed on them. So it says it vibrates at 440 vibrations per second or 500 vibrations per second. And then the tuning fork, tells you what the vibration is. And the longer ones vibrate slower, the shorter ones vibrate faster. Other things that might vibrate, even buildings. So this is a GIF of buildings. This is an earthquake in Japan, and the buildings vibrate back and forth with the frequency from either an earthquake, and sometimes this happens with wind, but it's not always as pronounced with wind. So I get natural frequencies. Now you can also magnify or amplify the natural frequency with resonance. So with resonance, you get the force that matches the natural frequency. If the force matches the natural frequency, I then result in greater amplitude. So what happens there? So this could be a bad thing because of earthquakes. So this is the Tacoma Narrow Bridge in Washington, and there were winds that were matching the natural frequency of the bridge. So I got tremendous swaying on the bridge. There's other ways for resonance. So a glass that breaks, your cartoon showed that the glass breaks when you sing really loud. It's not just really loud, but it's also really loud at the correct frequency. So the frequency that you sing at has to actually match the natural frequency of that fine crystal or glass in order to do it. Yes, you need high amplitude, but more importantly, you also need the right frequency. Another great example of resonance is pushing somebody on a swing set. So if you push somebody as they swing, they go higher and higher. Okay, so your force matches the frequency of the swing, and it increases the amplitude of the child that's swinging. But if you were to push the person when they were down at the bottom part and they were swinging back to you, then your force would not match that natural frequency. And if that was the case, then the swinger would not go any higher. So we know just from experience in our lives that what the correct timing is. But if we were incorrect timing, then the resonance doesn't occur. So the resonance only occurs when the force increases or amplifies the amplitude. That's it.